In this video, I will go through the tutorial Post-Layout Workflow, how to simulate a half-bridge buck converter in ADS-PEPro. On the PCB, there are just a few components to keep it simple. This layout can come from any CAD system, but I created it in ADS layout and exported an ODB++ file to have an example. Before you start, please make sure that you have the zip file, the buck post layout underscore tutorial. If not, just visit the Knowledge Center and download it from this website. You find there the guidelines, the ODB++, and two different libraries. In ADS, you can build up a simulation library which includes your components and also the technology. During the import, you can assign the simulation library, and therefore, after the import, you have already all simulation models assigned, and you can just start with your analysis. The reason why I have two simulation libraries is when you want to have a quick overview of the design flow. Then you can use the my_cmp sim_tech library, which contains already all simulation models. So when you start with a new design, it always happens that some simulation models are not yet in the simulation library, and therefore you have to manually assign it. So with this library, you will learn how to assign the most complex models like a FET transistor, gate driver, controller, and one capacitor, a simulation model. First, I create a new workspace without technology. To go faster through the video, I have decided to attach the simulation library where I have already all simulation models assigned. You can simply add any libraries with the menu Manage Libraries, but the same menu is also in Design Kits Manage Libraries. I prefer to use the menu Pick Manage Favorite Design Kits. lib.devs is for read only, but here this is for editing, that you are allowed to write more components into the library. In Manage Favorite Design Kits, I will choose Add Library Definition Files and choose the directory. Here I will use my component SimTech, which contains all simulation models what we have on our buck converter. So I take the definition file for editing, that I'm able later to add more simulation models to this library. I accept that this library is added to the favorite and add this to the workspace. So now when you look into the library view, we see we have two different libraries added to the workspace. The components library and the technology. So you can also have certain technology where you have also your material data, your layer definitions, and so on. To the component what we use in the tutorial, there are already simulation models assigned. You see it here. So it's a schematic view and a symbol view. But there are also some others components like the C22. It's not used in the analysis, therefore there's only a layout view. In this tutorial, I will use a design guide for power electronics, and therefore you have to install it. This link leads you to the Knowledge Center. Here you find the design guide files, videos, and documents. In the tutorial, we will use the basic templates for power electronics. So you have to install this .deb file. There you find this PDF with the guidelines how to install it. In the next step, we will import the ODB++ file from the ADS main window, import design. And here we choose ODB++ file format. And then we have to choose the file. This is the bug_layout tutorial. And then choose options. In options, we can now decide if you want to create new libraries for the components and for the technology. But I have already an existing simulation library, and therefore I point here to my component SimLib. And the same also for the technology. So you see here, I have added this with lib.des file in favorites. Next, I go to components. This is not my favorite here. I always use ODB++ part names. So, and I forgot something here. Don't forget to add new components, because it can happen that the new components on your new designs are not yet in the simulation library, and therefore the importer adds the new components to your library. So this setup is now okay. Here you can also decide which library name you want to have. For example, you just take the library name back and here only layout. And then click OK. Now the importer finished successfully. So when you don't have a simulation library, you just use the default create library and create technology, that you get the 3 libraries into your workspace imported. In fact, you get the same library structure. Here is a library with the top layout design, the components, but the components will have only a layout view, no simulation view. So you have to add manually to each cell a schematic view and a symbol view. And in the schematic view, you have to add a simulation model. So you can build up a library step by step. So you have start with the first design, you have a number of components, then you import the second design, then the second design adds again a number of components and so on. And so you also add the simulation model. You can also copy these libraries to any place in your database and add this lib.des file that you are able to add it to any workspace. There are just a few lines what you have to add in this file. So this file is shared, and this is necessary for the ODB++ importer that he can write into this library. Probably I should remove this read-only option because it does not really make sense for the ODB++ importer. So in this tutorial, all simulation models are already assigned. The importer has created a nice structure in the folder view. So all components are moved into the folder My Components SimLib. And here we have the top layout. So you can also choose any component and push to the component. And if you want to see if there is a simulation model, then just go to Window, Schematic. And so we see a simulation model is available. This is a layout view in ADS. So when you have attached the my_cmp simtech library, then all simulation models are already set up, and then you should just continue with your analysis. When you have used the tutorial library, then you have to add for 5 component simulation models. I will give you a quick insight how to assign simulation models. So when you have a large design and then you search for a component which you want to add a simulation model, you just choose the navigator here. If you don't see here's the navigator, make here a right mouse click and add the navigator here to this area. So you can switch between parts, navigators, and layers. So I type here C22. Click on this component. The location of C22 is here. And then push into the component, and now you see this is my footprint. You can check, is there a model available? There's no model because it doesn't open. So we go to schematic because I want to synchronize the pins from a layout view to the schematic view. Now it is synchronized and we can add a simulation model. There are several possibilities to add a model. So you can use a palette to have any behavior model. You can go to the download libraries to check out the vendor's web page. And here you are lead to the Keysight website, and this shows you which vendor does provide libraries or design kits for ADS. For the transistor models, you have to download a SPICE model. Just go to File, Import, Design, and then you see here we have several options: PSpice, LT-Spice, Spectre, HSpice, Spice 2G, and Spice 3. So we can also add the model as a netlist or as schematic, but netlist is recommended. To make it simple, I just type here SRLC, place the component, and define the values. It's also possible to parameterize it. I will also go quickly through the other components, such as the MOSFET transistor, the gate driver, and the controller. The transistor models have been assigned with the same method. I search for Q1, push into the component. In a standard installation, these icons are here in this area. I just moved it here around. So when you click here on these dots, then you can just move it where you like to have it. Then choose Generate Update Schematic. This synchronizes the pins to a schematic view. But here I have already placed the SPICE models, which has only 3 pins, but the footprint in the layout has 9 pins. So 1 pin at the gate, 5 pins at the drain, and 3 pins at the source. To make sure the current is evenly distributed over all pins, we have to connect here at the drain all pins in the schematic model together, and the same for the source at the switch node. I would also like to draw your attention to the fact that when synchronizing the pins from the layout to the schematic, a wire label is added to each pin, P4, P5, and so on. The problem here is when you have different wire labels at the same connection, the pins are disconnected from the transistor, and therefore you have to delete this wire label. So when I delete now this wire label, this pin is now connected and this cross disappears. The same you have to do also for this one and this. Now all pins are connected. This is just a simple model from the power electronic library. In reality, you would use here a SPICE model to check if the pins are correctly connected to the layout. In the layout view, pop out from the component view to the top layout and control the pins. Here at the gate, we have P2. At the switch node, we have P9, P8, and P3, and here are the drain pins. When you make here on the frame a right mouse click, then you can activate the display palette, and then you get here these icons, and then you can toggle the names, the numbers, and also the net names. I recommend before you continue, please first test your simulation model. You can get here the curve tracer from the basic templates for power electronics design guide in Add Templates Curve Tracer. Then it adds here this circuit, but you just exchange your device under test, define the parameter, run a simulation, and then you see in the data if it works or not. The same you have to do so for the gate driver and the controller. You can also click here when you know which component you want to choose. Push into the component, click on schematic, generate update, add the spice model or behavior model, and create a symbol. In the document, you find more information how the gate driver is connected, and the same for the controller. With the ADS layout, you get the full layout editor. So you can change the layout structure, you can add components, delete or deactivate components, or modify the substrate. On the left side in the layout window, you can choose between parts, navigator, and layers. So you can just make some layers visible or invisible. The layers can be viewed layer by layer with the menu view, layer view by name. This is the cont layer, which is on the top, where all components are mounted. Con 2 is a ground layer, a solid metal layer. But in reality, it is a current return path. PC1 is a wiring layer, and PC2 is at the button and again a current return path. Each structure in the layout should have a meaningful net name. It makes the simulation setup easier. The net names are already assigned in the original CAD system, but you can also assign it in ADS. When you click on a structure and go here on the right side to Properties, and then you can just choose here a proper net name. So each structure has its own net name. This is V1, here we have VN2, this is VSS, the ground return, and here's the V out, and this is a switch node. It also possible to visualize a net name on the structure when you click here on this icon, and when we zoom in, and then we see here the net names. I would also recommend enabling the layout command line editor. In a default installation, you don't see all these icons, what you see here in my environment at the top and at the bottom. When you want to enable it, choose Tools, App Manager, and enable here this layout command line editor. Restart ADS, and afterwards you just make here a right mouse click and enable the layout command line editor. Then you get the additional features, so you have quick access to the snapping function and also here to the fast grid spacing tool. With the layout command line editor, you can get great features in schematic as well. From the add-on menu, you can quickly make the pin names, the pin numbers, and connect the pins visible in schematic. To have a quick access to this feature, I have added a custom toolbar in Options, Hotkey Toolbar Configuration, and there I added a new toolbar group with the name Custom, and there added the icons. This is a very helpful feature because you should always know how the components pins are connected in the layout to ensure that the simulation model is also properly connected. Here, for example, LE is at pin 2 And when we look here in the layout, so we see here also the pin 2. So if this number is hidden, it is difficult to find. You can also click on the net and then you see it is probably connected. And so you can verify how to connect the SPICE model to the layout footprint. I often see SPICE models, they have a complete different pin sequence than the footprint. Before proceeding with the EM simulation, I recommend that you first create a schematic-only simulation to ensure that all simulation models work. It also provides a good overview of which components are needed for the analysis. If you start with a complex design without this test right away with the layout, it is more difficult to find the cause if a component is missing or a simulation model is set incorrectly. So if the schematic-only simulation works, you can be sure that the EM co-simulation will also work. As PEPro uses the same components that you have in your schematic-only simulation. When you create your schematic, do not use any components other than those mounted on your PCB. ADS offers a great possibility to create a schematic from the layout. I will only show this method in the last part of the video, as we already have a verified simulation library for this tutorial that we have assigned to the workspace during the ODB++ import. But this is a fundamental step that should not be skipped under any circumstances. It will save you a lot of time if something goes wrong. Now it's time to start PEPro. Either you click here on the P icon or choose Tools, PEPro, and then click on New. You can assign different substrates. Click OK. PEPro generates the 3D structure from the layers and the substrate. So the substrate is a third dimension. In analysis, you can create different analysis types. So you create a parasitic extraction for all nets. That means everything will be simulated. The second option is to create a new parasitic extraction selected nets. That means only the nets which you have selected will be simulated. Or you create a new SMPS performance test bench or a thermal analysis. In the tutorial, I don't include the components for a closed loop analysis. So we will use the selected nets analysis. Therefore, I changed here the name. And the other I will delete. For a selected net analysis, I also have to add the nets and the components. When you make analysis for everything, then you only add the components and the ports. First, I will assign the nets. You can assign a net as switching, power, ground, or undefined. When you choose switching, then the symbol becomes yellow. When you choose power, then it is red, ground is black, and unassigned turquoise. To have a faster EM simulation, I will assign all nets to power, except the VSS is a ground, and the unlabeled we don't use is undefined. Power nets and switching nets are very similar, but the mesh for power nets is more simplified for the EM simulation, and therefore the simulation runs much faster. So I would recommend in the first draft use power nets and for verification switching. You can explore your layout in more detail. In Conductors and Visibility, click on Hide and then choose any net when you want to see where is the location of that net. Here on that button, you can also toggle the component on and off. There are several options how to create analysis. So you can drag and drop the net to the analysis, or you drag and drop the components to the analysis. But you can also select the component on the layout. Press the Control key and the left mouse button. And drag and drop it to the component models. Here you see all nets which are connected to a component are automatically added to the analysis. For a more complex design, it is better to add the nets to the analysis. So here an example, I choose the VIN2 net and the VSS net and add this to the test analysis. Choose both nets, make a right mouse click, and now it finds all the components which are connected to these two nets. So I just drag and drop it into the component list. Now I have all this model added to the analysis. As next, I will check how the components ports are constructed by PEPro. And let's have a look to the MOSFET model. At the beginning, I assigned the switching nets to a power net and VSS to a ground net. So PEPro can now figure out where are the plus pins and where are the minus pins. Pins are connected to power or switching nets are assigned to plus pins. In pins assigned to a ground pins are minus pins. For this case, the MOSFET model becomes a 6-port component. P3, P8 and P9 is a shared ground reference pin. So when we have assigned net rows, power or switching and ground, then PEPro can find for each component where is the ground reference. Just have a look on the power choke. So this is actually a long port. So the plus pin is here and the minus pin is the other one. So that means here the current flows in, the current flows out. But what happened here in the return path? And on the other side, this component becomes now a 1-port component. Underneath each component pin is a metal which is on a ground net, second layer 2. So PEPro can automatically generate a virtual minus pin at the same X and Y coordinate on the layer con2, which is the current return or the so-called ground net. We must be aware that RF signals are generated in an SMPS converter, and therefore we need a good model for the current return. In this design, we have the advantage that underneath the components is a solid current return net. In PEPro, we can define reference pins in a layer. Right mouse click and then create reference pin on a layer. And I choose Con2. Back now to the discussion of the power choke. So this is at the moment a 1-port component. But I want to have here a 2-port component. So I just drag and drop this reference pin to the power choke. And now I can make this component as a 2-port component. Now we have 2 reference pins for this component, for pin 1 and pin 2. Actually, it is easier to delete all components and add again to the analysis. to assign this reference pin to each model group. And now when I open one component, then we see it automatically takes the reference pin if it is defined. Unfortunately, the reference pins on the reference layer are not visible because they are generated temporarily when the mesh is generated. But we know at each x and y coordinate of each pin is a reference pin. You should also check if each reference pin lands on a coupler and not on a clearance or a cutout. First, select the components to see the pins, and then go to Substrate, Conductors. And now we can just make all other layers invisible. So we can see at each pin we have a solid metal, and we can continue with this setup. To make all visible again, click in Conductor to Solid. Oops, I just noticed the controller is not in the setup. So I also need to add the controller model to the component model group. Otherwise, my co-simulation wouldn't work later. So the next step is to add input and output ports. In the ADS layout, there are already connectors for V in P and V in N, and the same for the output available. So in the design tree, in components, you find the connectors. And then we choose the first pin, the V in plus, and drag and drop it to the ports. So we see here now, we have here a plus minus port. Better is you change this, that you have only V in P, a useful name, and the same we do for the V in N. So now we run into the problem that the PEPro assigns the V in N as a minus pin, and therefore we delete the plus pin and change the polarity and take here the reference. And at the end we also change the name. This is now the V in N and the same we do for V out N and V out P. Now it is done. You notice here also there is a warning that we have some nets in the analysis which are not connected to anything. You can delete these nets if you want, but it doesn't matter if they are in the analysis. You can also check the ports if they are landed on metal. Either you use here this scaling for the z-axis. Now we see all is okay. Or you can use the other method that you just make the other layers invisible. Everything is okay. Finally, we define in option the frequency plan. So we have here 250 kilohertz, and we use a rise time of 10 nanoseconds. And the near field and far field is at that moment off. So we just run the simulation. Now you see here, this is the status window. In the status window, you can look to the summary and also to the log file. This design runs very quickly through. On my PC, it is, I think, less than 2 minutes or so. Okay, it took 55 seconds. So the next step is now I create a subcircuit. Just double click here, create new cell. So PEPro automatically connected the layout with the components together to have a full co-simulation setup. Next step is to connect this subcircuit to a template from the design guide. Therefore, I go to Design Guide. I choose here Basic Templates for Power Electronics. So first time when I use this design guide, I have to copy a couple of files into the workspace. You have to do this only one time for each workspace you use this design guide. A good method is to copy the cell name into the buffer. Select the name and Ctrl+C. And then I go back to the design guide, basic templates, and choose here the buck half bridge with VT pulse. I still have the subcircuit name in the buffer and paste it to the search field and place the subcircuit. Here we have this symbol, pin wire. When I click on this pin wire, it automatically connects my device under test with the template. This is the reason why I use here the same pin names in PEPro what I have in my template. The only what I want to change here, let's say we have here 15 nanoseconds rise and fall time. V in is 48 volt and V out is 13 volt. And for the first run, 40 cycles are enough. Inside this box, there are probes which I will connect inside the subcircuit. These probes have a wire label which are used later in the data display. Just copy and paste these probes into this subcircuit. And activate. These three probes are for the high side and this for the low side transistor. There are several ways how to connect it to the transistor. My favorite is to just copy the wire labels. To copy a wire with a wire label, you have to click on the wire. Ctrl+C and then Ctrl+V. Connect it to the transistors. Gate, source, this is the drain. And the same for the second transistor. And here are the probes to connect the gate driver. So I need to copy the 4 wires from U1, Ctrl+C, Ctrl+V, and connect it here to the probes. Save and go back to the top hierarchy and run the simulation. When the simulation has finished, ADS writes a dataset and opens a data display. So in this data display, I have used the wire labels from the probes, which makes it possible to have a preconfigured data display. With the slider N last cycles, you can decide how many cycles you want to have in this plot. So we view here 7 cycles. When you want to shift the cycles to another time, change it with the marker cycle N. And now it is shifted on the time axis. On page 3 is a rise and fall time analyzer. You can control what you want to display. 90, 10%. Then you type here the rise factor is 90 minus 10. When you want to have 80, 20%, then you have to type 80 minus 20. The first what you need to do is to move the marker Shift 2 to have the data centered. That you have here the pulse in the center, low on the left and right. It also possible to view the cycles along the time axis. Here we see the cycle number 149. When I move it here, then it is at 87. The markers left, mid and right control all these markers. So don't move here these markers, then the connection to this marker is broken. So I need to move here the marker left to the left, here to the mid, that you be here in the area of high, and the right to the right. And then you see in each plot rise and fall time. Here inside this rectangle is the gate source voltage for the rise and fall time for the high side, and this is for the low side, gate source voltage. Inside this rectangle is the drain source voltage for high side and low side. On page 1 I noticed that the current at the power inductor is missing, so I forgot inside the subcircuit to connect the probe. Now the data for the current at the power inductor is available. Please also have a look at the Knowledge Center. Here you find videos how to use the power electronics examples and templates. Next step is to run a conducted EMI simulation. In a conducted EMI simulation, we can capture the total, differential and the common mode noise, which is measured with an EMI receiver at listen 1 and listen 2. In simulation, we have here a 50 ohm load resistor and calculate the noise using the measurement expression from ADS. This is an overview of the simulation and measurement setup. So we have 2 listens for the plus and minus line, which are placed on the common ground on the top table. In ADS we have circuit models in the PE library. In the simulation we model the wire between the listen and the device under test with a simple inductor. According to CISPR, the distance between the PCB and the common ground must be 10 cm. To keep this distance constant, the styrofoam is used. To model this in simulation, we just add here an air layer of 10 cm. Additionally, we will add a conductor and cover at the bottom of the substrate to model the common ground on the table. In the previous simulation, all ports on the PCB were defined differential, while the reference layer was contour. The only what we have to change from the previous PEPro setup are the input ports that we use here a different reference. In measurement, the common ground is the top table, and in simulation, it is the cover. First, I will save the layout cell with another name. The substrate must be also changed to include the styrofoam to model the measurement setup. Save it with a new name. Add cover for the common ground and add the styrofoam as air layer. The thickness is 10 cm. And save it. The next step is to assign the new substrate to the new layout PEPro setup. Just make here a right mouse click, configure PEPro setup and choose the new substrate. OK. And then start the PEPro environment. Now you can also check when you click here on properties. So we see now we have the new substrate assigned. This PEPro view is now a copy of the previous simulation. So all ports are referenced to cont layer 2, the yellow layer. But now for a conducted EMI simulation, we need to reference the input pin for the plus pin and the minus pin to the cover of the substrate to include the common mode noise into the simulation model. When PEPro finds a cover in the substrate, it automatically adds a reference pin on the cover. So we just need to drag and drop this pin to the port and here as well. But we also need to delete the reference pin on contour for both ports. In the previous simulation, I have forgot to remove the unconnected pads. So you see here, there are pads which are not connected to anything. And this should be removed because they are not in the real PCB. To remove it, make a right mouse click on this black layout symbol. And then choose unconnected pad removal options and activate enable. Apply, done. And now you see the unconnected pads are gone. All other options are okay and we just run the simulation. So the simulation has been finished. So you see it is also faster than the previous one because I also removed now the unconnected pads. The next step is to create a subcircuit. On the left side is the subcircuit of my first simulation. On the right side is the subcircuit of the conducted EMI simulation. So I want to copy and paste the probes from the first simulation to the new one. Therefore, I delete here this power choke and copy and paste this probes subcircuit. From the design guide menu, Power Electronic Templates, choose Template and then Conducted EMI test bench and insert the subcircuit. The subcircuit is not yet connected to the load. I have to change here the wire label. V load for plus and minus. Change the parameters. and run the simulation. So now we have all the data in the data display. So everything is pre-configured because I have used the probes in the subcircuit and use here the names from the probes. Here we have the total noise, differential noise, and common mode noise. The other plots are similar what I showed earlier in this video. When you want to simulate the near field, make a copy from the analysis. Copy to duplicate. First I change the name and then define the frequencies of interest and run the simulation. When the simulation has finished, open the near-field viewer and then apply the transient simulation from the conducted EMI simulation. First choose excitation type and then circuit simulation data. Navigate to the data directory in the workspace and choose the dataset from conducted EMI simulation. When you see here this green check marks, then you know that the transient simulation is a valid dataset for the circuit excitation. PEPro applies at each pin the voltage and the phase to the electromagnetic field to get the surface currents of the PCB for each layer. Choose the frequency and the layers of interest, scale the Z-axis and look between the layers. But it's also possible to view layer by layer. Next I will show how to simulate radiated EMI. But I will not do the simulation in this PEPro setup. In a radiated EMI simulation, I assume that my PCB is far away from ground, and therefore I will not include the styrofoam in the simulation. So I can reuse my first simulation. Here again, I make a copy of my analysis. Copy to duplicate and call it A1 underscore far field. Nothing has changed in this setup. The only what I have to change is the simulator, because momentum RF doesn't calculate the far fields, and therefore I switch from momentum RF to momentum microwave, and in the frequency plan I start from 30 MHz to 300 MHz with 28 points. So there's no need to calculate more frequencies below 30 MHz. For the far field calculation, I would recommend to enable only the far fields, not the near fields, because the near field takes some disk space. In the circuit co-simulation, we need all these frequencies to cover many harmonics. For a radiated EMI simulation, we just choose a frequency band of interest. Now we can run the simulation. When the simulation has finished, we can open the far field viewer. So we get here the far field, and then we will also apply the dataset from the transient co-simulation. Here I have to use the dataset from my first co-simulation. Now we can also create the EMI graph. As next I have an optional topic, how to create a schematic only simulation from ODB++ import to test the simulation models. In this tutorial we use a very simple PCB which is quite practical for this exercise. I'm sure that your PCB is much more complex, and for that I would like to provide some guidelines. With the ODB++ import, we already had a library of simulation models, but when you start with ADS, you don't have one. So I will show you a workflow that works best. Consider which components are really needed for the SMPS circuit in the analysis. Do not add any components that do not have any influence on the circuit. These components would only increase the complexity of the analysis. So the ODB++ importer created three libraries. One library where you have the top layout cell, one library with component cells, and one with the technology. When you start with ADS, all component cells will only have a layout view. So you have to add a schematic view with simulation models and a symbol view. So in step 3, assign the simulation models to the required components what you have figured out in step 2. To ensure that all models work correctly, first create a schematic-only simulation. Use the components from the ODB++ import, which you have already assigned in the previous step. This is the optional topic in this tutorial, but I will show it in more details after this slide. Start PEPro and add the components to a selected net analysis. PEPro automatically pick up the simulation model from the component cell. Check the component port in each model group, in particular whether the reference pin is defined correctly. Define the SMPS sweep and start simulation. When the simulation has finished, create a subcircuit. PEPro automatically connects all components with the layout together to form a co-simulation setup for transient shooting or harmonic balance simulation. Step 7. Open a template from the design guide for power electronics. Insert the subcircuit, connect it and run the simulation. The templates from the design guide contains pre-configured schematic simulation setups and data displays. Now I will provide more insight how to create a schematic-only simulation from ODB++ import. I would recommend to save the top layout with a new name. Save as, make it simple, L2S, layout to schematic. So this new cell only has a layout view. ADS has the feature that we can synchronize a layout to a schematic or schematic to a layout. Next step is to create a schematic view to this cell. There are several ways, but I prefer to use this method. In the layout, choose window, choose schematic, and just create schematic. So now I have here also a schematic view in this cell. In my ADS environment, you see here these docking windows. So you can activate these docking windows when you make here a right mouse click or go to view and activate the docking windows. But I did it here, right mouse click, and here I activated differences from layout. So you just drag and drop the components from the list to the drawing area. So in the rubber bands, indicate which components are connected together. In the document, there are guidelines step by step. I would recommend to place here pins and connect it with wire labels and create a symbol. that you have the same symbol what you usually get from PEPro. I also would use the same port names and port numbers what you have in your PEPro setup. Don't forget to add the probes, because this ensures that your data goes directly into the data display. You can get the probes from the basic templates for power electronics, either from here, from the templates, or from add components and subcircuits, all voltage probes. And then you just add it. This is the same template what I have used earlier in this tutorial. Replace the subcircuit and run the simulation. Here I use the same template in the data display. The left plot is the drain source voltage. The red trace is with layout and blue is without layout. And right is at the switch node. So we see here the layout effect due to inductance and resonances. I hope with this tutorial and video I have provided you enough information so that you can successfully simulate your own design. I also hope I could show you something new and you have enjoyed the video. Thank you for using ADS for power electronics.